Okay, hello. Dr. Taylor here, fifth lesson in limits section. And we're going to look at infinite limits. That's limits as x, your input value, approaches infinity. So as x gets infinitely large, or negative infinity, infinitely small, what happens to the overall output of the function? Does it go to infinity, negative infinity? Does it go to a discrete value? That's what we're going to find out. Infinity is kind of a weird thing to think about. And we're playing with infinite, getting infinitely closer to something, that's a limit. Now we're thinking about getting infinitely large or small as an input value, which is another way that infinity comes into calculus. So, let's begin. Let's take a look at this function. Alright, so I want you to see something here. I went ahead and put it up with the work. The limit as 1 over x minus 1 over x minus 1 as x approaches infinity. So we want to think about that little bit of construct we talked about, why an asymptote was called an infinite discontinuity, right? Because 1 over 0 meant that 0 could be divided into 1 forever, and I would never fill the 1 up with zeros to get to its limit. How many zeros does 1 hold? It holds an infinite number of zeros, okay? So now, let's think about that. If I let x be infinity, okay, and I think I'd like a little bit more of a breakdown here. So let me clone this, and let me take off a little bit of this, okay? As x approaches infinity, you can see that this piece right here, that isn't that important. And I like to talk about it this way. If I'm carrying $1 million, how about 1,000 million, $1 billion in a big pile, and I'm carrying it home, and if I get it home safely, I get to keep it, and $1 blows off my pile, do I stop in anguish and go back and try to get that dollar because now I've lost $1, man? Or do I carry my 1 billion minus $1 home and feel perfectly happy about it? Well, that's what I would do. That's what I would do. I would feel perfectly happy to lose that $1 because it's so insignificant in the billion pile. I will make that up in interest and then some in the first moments of putting that money into some account. So that $1 isn't that critical to either subtract or add, for that matter, when your number is really, really huge or really, really small. Okay? So, and when I mean really, really small, I don't mean 1/2. I mean like -1 billion. If I add $1, if I owe you $1 billion and I say, well, look, man, here, I'll start you out. Here's $1. Now you owe me $1 billion minus 1. That's not that important. I still owe you $1 billion and I don't know what I'm going to do. All right? So this is why I've got this circled and starred here. So what we're going to do is we're going to kind of ignore that. Not that it's not important, but to evaluate this, when we're looking at as x goes to infinity, the 1 isn't that important. So now I've got 1 over infinity divided by infinity over 1. And why did I put it over 1? Because x is infinity. Because this is basically a fraction divided by a fraction when I ignore that part, right? But my focus is here. I make this a fraction so that I can do the elementary school algorithm of fraction divided by fraction. You know, keep, change, flip, whatever it was you learned. What I like to say is it's this divided by that. And the word that is what gets inverted. It's what the reciprocal becomes. It's the divisor. Whether we left to right or top to bottom. This divided by that. That gets flipped. I can't flip it if there's no bottom. So I put the whole number over 1. Now I can flip that. Okay, wait a second. Where did my numbers go? Oh, there they are. There. So now I can flip that. And when I flip that over, right, it's no longer here. Now I have 1 over infinity times 1 over infinity, which equals 1 times 1, and infinity times infinity. Well, infinity squared, that's not much of a notion, right? That's really not much of a notion. Infinity squared, you could just say that's 1 over infinity, right? Because infinity is so large I can't think of it. When I square that number, it's just a large number. So infinity, it's a concept. There's no such thing as infinity squared, okay? And so since there's no such thing as infinity squared, then I can just consider that as 1 over infinity. Now, so I'm thinking about 1 over infinity. And I'm asking myself a question. What the heck does that mean? All right? Well, I got 1 over 0, right? We said 1 over 0 is infinity, right? So that's kind of like 1 over 0, right? But what is 1 over infinity? Well, that's not so hard to figure out. Let's buy a pizza. And what I'm going to do is going to cut that one pizza into 2 pieces. And I'm going to give you one of them, and I'm going to take what's left. So we each get 1/2 of a pizza, right? Now I'm going to take that pizza. I haven't given you your piece yet. I'm going to cut that in half again. Now it's 4 pieces. I'm going to give you 1 piece and keep the rest. Now you get 1/4, which doesn't make you as happy because you paid half the money with me. If I say, wait, let's cut it in half and half again. Let's make it in 1/8. Now I give you 1 piece. You get 1/8 and I get the other 7/8. So you see what's happening? The bigger that bottom number gets, the less you get. If I cut it into 1,000,000 pieces, you're getting this little grease sliver. If I cut it into 1,000,000,000 pieces, maybe you're getting a couple of atoms. I'm still getting the rest of the pizza minus the 1/1000,000th amount that I gave to you. So as that number gets very, very big, you get closer and closer to getting nothing. And so what happens is 1 over infinity is equal to 0. Its limit is equal to 0. Do I ever get to 0? No. Because I've got 1 something, but that piece gets to be so small that it effectively is approaching 0. Again, it's that limit kind of mentality. So 1 over 0 is infinity, but 1 over infinity is 0. So that inverse relationship really kind of kicks in. Okay? So let's look at this one. If I'm doing this one, again, I'm ignoring these numbers because when I go to infinity, 4 or 2 doesn't much matter. And I'm able to ignore these numbers because of something called L'Hopital's rule. And we'll talk about what that is in a second. So when I ignore those, I just have infinity over the square root of infinity. Okay? So if I think about this and I change it to exponential statements, infinity to the 1 divided by infinity to the half means I flip this up, but because I flip it, the exponent changes to a negative. Or if I just did 1 divided by 1/2, right? That'd be 1 minus 1/2, because when I divide like bases, I subtract the exponents. However it makes sense to you, it's just the rules of exponent. I end up with infinity to the 1/2, or the square root of infinity, right? Oops. Oh, my bad. So the square root of infinity. Now, what is the square root of infinity? I could say, just like I said infinity squared is infinity, I could say the square root of infinity is infinity, right? And when I do that, what I am basically saying is it has no limit. Remember? Infinity isn't a number. So the square root of a non-number is still just a concept I can't put a dot on. So if I got infinity squared or the square root of infinity or just infinity, what I want you to see is no matter how infinity comes out in the end, if your answer is infinity, and it's unreducible and unchangeable and I can't figure out any other way to do it, then I accept it. I could check it with a table. And so that's what I'd like you to do. Check it with a table, and you tell me whether it has a limit or whether it has no limit. And you can send me that answer in the homework that you email to me. All right. Let's look at this with factoring and canceling. We could have infinite limits with factoring and canceling, right? So here's one, a polynomial on top and a polynomial on bottom, all right? Now, what I'm not doing is saying this cancels that. No, I'm not. I'm saying whatever x is the infinity, right? Whatever power I raise that infinity to, that just means it's approaching infinity faster than if it was going to the third or the second or the first power. So just like 1 didn't matter much, when I have a multiplicity of infinities, the only one that matters really, the one that really drives the function, is the highest order power. So I can literally ignore, not canceling, okay, not canceling, but ignoring. Okay? Very, very important. Not canceling, ignoring. Now I can say, look, if they have the same power, I can analyze them as, I don't care if it's infinity, it's still x. What's any number over itself? 1. So now what it boils down to is the coefficients of those common values, well, they are the answer. 3/4 times 1 is 3/4. Bang. I can't tell you why L'Hopital's rule works yet, because we haven't talked about what a derivative is. And all L'Hopital's rule is taking a derivative to the top and the bottom over and over again until I eliminate all the x values in at least one, the numerator or the denominator, and possibly both, as this would be, those both canceled. I just had to have just numbers. Okay? That's what L'Hopital's rule is. But we're going to functionally use it by saying only when it's x goes to infinity do these rules apply. And that's where people make their mistake. Oh, that's easy, and they want to do it everywhere. It's easy, but it's rarely usable. Okay? In the rare occasions you can use this easy one, use it. That's what I'm saying. Okay? So, this kind of graph, and this is not, I'm just looking at this graph saying, you know, look, there's all kinds, I could have a bunch of asymptotes, right? So I could have a horizontal and a vertical and whatever, okay? So this isn't a graph that says this is what this is, but this is saying that no matter what, you know, there are limits that exist in certain regions and not in others, okay? All right, so this is your work, right? I want you to take 2, 3, 4 minutes and do it, and then we will, I believe, yes, look at it together. All right, go. Okay, welcome back. Here we are. Now, if you're just watching this, I probably look schizophrenic, but you know, you were supposed to pause it and try it in that gap time, so if you didn't, shame on you. Okay, if you don't think before you watch and listen, then answers with no thinking is no retention, so that's not going to help. All right, so when we're working, and I say put an x in for infinity, right? Let's just do that. Let's put an x in for infinity. Infinity over 1, infinity over infinity, and 1 over infinity. Now we know what infinity over 1 is. It's just a whole number, right? It's infinity. And we talked about what 1 over infinity, if I cut the pizza up into an infinitely large number of pieces, those pieces will become infinitely smaller until I get virtually nothing. So this is 0. That's infinity, and that is nothing. Okay? But what is infinity over itself? Well, that's something we looked at in the last problem. Since this is not x squared over x to the 1 or x to the 2 over x to the 3, this is x and x. That means it's growing to infinity at an equal rate all the time. So no matter what point in time I examine it, it's going to be a number over itself. No matter when. No matter what. So this is no limit. This is a limit of 1, or a constant, whatever that constant in front would be. In this case, it's just 1. And this is nothing. I don't care what that is. If it's 2 or 5 or 10 or 1,000, when I divide it by infinity, it's nothing. If you get 1,000 pieces of 1/100 billion trillionth of a pizza, you still got nothing, right? So it's about what's on bottom that makes this worth nothing. Okay? So let's look at this. And again, this is not the book you're in, all right? So f of x is equal to x squared minus 1 over x squared plus 1. Well, normally I would, you know, oh, can I factor that? No. Right? No, you can't. But since I'm looking at the limit as x goes to infinity of that function, what can I do? I can ignore what's not a variable. And if I have more than one variables, I can ignore all but the highest order variable on the top and do the same thing on the bottom. So I can ignore what's not a variable, that's the negative one and the positive one. And I could ignore all except the most high top and bottom value. Well, that's only one choice each, so basically I get x squared over itself, which is what? It is 1. And my limit is 1. It's powerful, isn't it? Makes it easy, right? This stuff's not hard. It's the algebra that's going to kill you, not the calculus. Okay? What if I went to negative infinity, right? Well, what happens when I square negative infinity? I get positive infinity. What happens if I cubed it? I get negative. What's negative over negative? 1. So no matter what, it doesn't matter. Just plug it in and think about what it would be based on signs when you raise them to a powers. Analyze it like you're algebraically thinking, because that's what you're doing, and give the value that it says. It's really that simple. All right. Now, this is what's called the difference quotient. This is what's going to lead us to something called the derivative. And this is where we're going to stop. I'm not going to tell you how to do this, but if you're smart and you try this and you expand and combine and blah, 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 and factor and cancel, you'll figure out what that is. And it will be a very powerful understanding. Okay? But this is not infinity, right? This is 0. Makes that undefined. Got to get rid of that. There's going to be a strategy to it. So this is a challenge. It's not an infinite limit. Infinite limits are easy. You can do those quickly. This is a challenge to get you ready for what comes next. This is Dr. Taylor saying, don't give up.